Good. Yeah, thank you. Okay, before we start, I would like to ask you about Lab 5, just to make sure things are going in an okay way. Is there any concerns you guys are facing or any problem or this week that is ending today? Hopefully it was more stable because the TA that is doing it is one of the remaining TAs we have after the strike. So is there any feedback you would like to share? Feel free to use the chat or just use the mic, whatever you feel more comfortable with. See if the bin is working. Okay, we should be good. Okay, maybe another question. Did anyone manage to finish Lab 5? I'm using the camera. My camera is on, but for some reason I don't see myself here. I'm able to. I'm assuming that you're able to see me. If that's the case, please confirm if it's otherwise. Okay, I see myself on. Okay, so maybe if you add a device, you don't see yourself on the other device. So Stefan, I'm having a hard time conceptualizing what a linked list is, which is, I think, making it more difficult. I see. Okay, so Stefan, I thought the past two lectures might have helped with this. No? So maybe my suggestion then, if that's the case, don't in fact start with Lab 5, but rather start with the examples we have in the past two lectures, right? This would be my suggestion: is forget about sets, because there's one extra step in Lab 5, which is in fact using linked lists as a data structure to implement the set, as we said before. So my suggestion is that if you are facing issues with linked list itself, then maybe go through the example we have done in the past two lectures, defining a linked list, declaring it, and using insertion, deletion, and searching. This might help a bit. Yeah. So okay, so now it's the other extra step, which is how you can use a linked list to implement the set, right? So the key to this is, in fact, a set is not a data structure, right? So it is, in fact, an abstract data type. So you can think of a set as an extra requirement on a linked list, right? For example, you want it to be sorted. Then, well, insertion in a sense and deletion would require some extra steps, right? Um, that's just the key idea, is that you have the linked list as is, but you add extra requirements. Say that the memory I am maxing is crashing. My program it doesn't off. The debugging tool gives the same thing. So Kurtz, this low level problem might be because of allocating a memory that you're not freeing. My suggestion is just go to the office hours and use them to track with the TA what is really the problem, where the allocation happens, and not freeing it, right? It might not be necessarily in your own coding, but might be in the test cases. I'm not very sure, right? But this is what I'm suspecting. If you get a memory crashing, it usually happens because of allocating a memory or trying to access a memory that's not being allocated. That's usually the case. Okay, so is there any other one want to share any further feedback before we start? Okay, so in today's topic, in fact, we are covering something that is, in a sense, one of the key features of C++, which is the STL library. What is STL library? So you guys, for example, are doing one whole lab to implement a set using a linked list, and you come up with your own linked lists. But think of practical industry programs or software that would like to implement well, I will give you an example for what we do in our research lab, for example. So let's say we are building a simulator that simulates multi-core architecture. So the pipeline, the cache hierarchy, the interconnects, what we do. So in fact, this is a practical example. In that case, you'll be using in fact needed. And given that most of the data structures are already well known and well studied, you got cut off. Is that the case? And others confirm, because I still see myself in both. Um, well, am I back now at least? Or you guys don't hear me at all? Okay, did you lose me already? We can't hear you. Okay, so that's interesting. Okay, so what I was saying is, I'm not sure from where did I was lost, but what I was saying is, let's have a practical example where you don't do what you do in the labs is just in terms of educational purposes. So we put enough emphasis on touching different aspects of programming, but generally you use software to model stuff, right? To implement a solution for a problem, or I gave you the example from our research lab where we use software to model architectures, to model multi-cores, to model cache hierarchies, to model main memories. And in that case, the focus should not be in fact, implementing your own data structures, because this will be a deviation from the actual project. And what I was saying also is asking every single system modeler or developer to implement their own data structure that they want to use seems impractical, in part because those data structures are already well known, well studied. So like providing them as a starting point seems a good application of the code reuse, right? And that's the main idea of the STL. The STL provides you with data structures, implementations, and algorithms that operate on these data structures that you can use later on in your own code, right? In part, implementing those STLs, what 2SH and 2SI would cover on is in fact learning how those are being implemented, right? And how to use them efficiently. But later on in if you go for an industry internship, or if a full-time work, or you do some research that use software modeling, in that case, you will be using these pre-built, already implemented data structures to do your own stuff, right? So this is the main purpose of having the STL library. So how did this STL library start? Well, in 1990, well, two engineers from HP, in fact, extended the C++ with a library of class functions and templates. So they used what we have discussed past lecture. This is why STL comes very natural after the template lecture, because the main starting point of STL, and this is what from the name, it's called Standard Template Library. Those two engineers use the template concept to implement different known algorithms and data structures and release them as part of the C++ library. Good. And then 4 years later, this was in fact adopted as part of the C++ standard. So it comes with every single C++ storage chain. What are the main components of the STL? What does it provide? It provides three main things. What we call containers, right? Now we use a different word than data structure, but in fact, containers are nothing other than data structures, right? And by the way, I'm looking here because I'm sharing now from desktop, not the tablet. So hopefully they are okay. So basically, what is a container? Is nothing other than a data structure, something like a linked list or a list or an array, for example. But because we don't really implement the data structure for a certain type, but we rather use templates or generic class templates, then STL call them containers, right? So what are containers? They are generically templates for data structures. Good. And then the second concept of STL is algorithms. We have seen that in linked lists, for example, when we implement a linked list, that's the data structure. You also want to implement some methods that operate on it, right? For example, searching it, sorting, deletion, insertion. Those are what we call algorithms, right? And we usually implement them as functions. Since we have implemented containers as templates, or class templates, then algorithms by default will be, well, function templates, right? For example, a generic function template for insertion or for deletion or for searching or for sorting, right? And then the third nice concept in STL is called an iterator. You can think of an iterator as an extension of a pointer, what here we usually people refer to as a smart pointer. So think of an array, for example. In an array, how do we iterate through an array? Through the index, right? So we have a for loop when you have seen this tens of times throughout the course, a loop starting from 0, go up until the array size and iterate one by one. But this only applies to an array, right? If you want to iterate through a linked list, well, we have seen this in past lecture, doing searching or traversing, for example. In that case, I need a pointer that starts from the head, go one by one until it reaches to the tail, right? What if I have a different data structure than a linked list? Then you need another way of iteration, right? So this neat idea of iterator is kind of extending pointers to apply to any container or to any data structure. So it becomes now independent of the data structure. It's very nice, and I will show you later on that's in fact very easy to use as well, because you use iterators as if you use indices for an arrays. Good. So these are the three main concepts of the STL: containers, algorithms, and iterators. One very important disclaimer before we go into details is I don't think by any means it's possible to cover STL in one lecture or two or three, right? Sometimes there are like half of a course that is really focusing on this. But I wanted first to give you at least a hands-on example and give you the keys that would allow some of you that might be interested to extend on. And also, if you have seen something in front of you, it doesn't seem weird, right? That's part of the C++ and you at least heard about it before. Maybe the most basic thing that was added in STL was the string abstraction. And this is the thing that we will start with. You remember from C is that we didn't have an inherent type called string, right? How did we implement strings in C? Does anyone remember? What do we do when we want to have strings in C?
You would implement an array of characters.
Exact. Thanks, Kurtz. That's array of characters was our starting point, but later on when we introduced pointers, we implemented them as a pointer to a character, right? Like you remember this? Like we had something like character pointer. And then we used it basically to also define strings. That's great. Thank you. So in C++, with the STL extension, they provided a class. Now we know classes, we know templates. Then we can use this class to implement a string, right? And this will be our starting point. So why to use STL? For different purposes. Well, it offers you different assortments of containers, data structures that are already implemented. It also offers to you what is the complexity, the runtime complexity. I kind of briefly mentioned this to you before when we compared arrays with linked lists. And the main focus of 2SI will also be on this, is the complexity of a container or a data structure or an algorithm. For example, we have what we call time complexity, which how much time you take to run a certain algorithm. This is usually referred to as the O notation. Again, that's covered in 2SI, so don't worry about it. And in addition to time, there is also how much space you take. Here is called storage complexity, or people sometimes refer to it as space complexity. For example, do you need an extra array to sort an array? We have gone through this example before. Something good about STL is that for every single container and every single algorithm, they tell you what is the time complexity and what is the space complexity. So it allows you to choose based on your own trade-offs. A third important thing is that because these are implemented as classes and templates, they are not static, right? So they grow and shrink in size automatically, right? You can insert, delete into them using basically pointers. They also provide built-in algorithms, as we have already mentioned before, to operate on. And they provide the iterators, which is the third main pillar of STL, as we have already discussed. It also, and that's something that is very interesting, the last point, STL offers users to also add their own containers. So you can define a container that in fact you can use later on and extend the STL basically with. So there is what we call user-defined algorithms or user-defined containers. And you can basically user-defined algorithms can be applied to already STL containers and the other way around. So it's very, very flexible. You can write your own algorithm that operates an already existing container, or you can write a brand new container and then the existing algorithms can operate on it. And very, very flexible. But let's start with the most basic thing, just to help us grasp really some of the concepts. So strings, again, like in C, we used character arrays or character pointers to represent strings. C++ already provided a string class abstraction that is named string. This allows us to go from that code in C, where I can define a string using a pointer, to do something like this in C++. I can just define a string type, my variable str, and then say equal, and then initialize it. How can I do this? Well, the key is here, including the header file string that comes from the STL. Right? So simply the idea is you need to include this, and then given that string is a class, I can in fact initialize it using different ways. I can initialize it using the equal operator or the assignment operator, or I can initialize it using this constructor. Well, now it doesn't seem weird, right? Because you really know that this is nothing other than a class, right? And you can also assign a string to another string. We can do the things that you guys have used to see in Python in first year, but we didn't see in C because it wasn't allowed. Now C++ brings it back by the extensions of the string class. There are also multiple things. Remember, we needed to write our own size or string length method. There is already a size method in the string class. Simply just say string dot size using the string as if it's just an object of a class, right? And it gives you the size. How this is possible, just again, because it is just a method of a class, right? If I already instantiated an object of the string class called str, I just deal with it as if it's a normal class, so I can use all the methods, and this is a public method to operate on my class, right? I can then do multiple things. I can, in fact, this might not be very clear, but that's a plus thing. I can do concatenation using plus. I can do assignment using equality. I can check equality by saying equal equal. Most of the things, again, you might already know from Python, right? Good. So all of this is basically allowed by using the string support in C++. Let me stop for a second. I know this might be things you might have already expected. You might have been shocked already that they don't exist in C, but then C++ brings them back. Before we delve into the actual meat of STL, let me stop for a second and see if you guys have any question related to using strings in C++. So the key idea is that strings now in C++ are no longer modeled as arrays of characters, but rather as an objects of classes, right? That's really the key, right? Make sense? I guess this seems like an intuitive idea, right? Why someone doesn't come up with a class called string and then add all the methods there and then we just use it, right? Okay, so hopefully that's straightforward. So now let's delve into what might be more involved with containers and algorithms. Some of the containers that you might already know, again, from Python, we have a list, which is implemented as a doubly linked list. We have a vector, which is pretty much similar to C array, but it's dynamic. So vector is the dynamic version of arrays. We have what we call a map. Usually map is a very well-known data structure that stores things in a pair of values, a key and a value, right? It's called a key value pair, right? Usually this is used for hashing. This is used for password usernames in databases. It has its own uses, right? For example, a student name and an ID. So maps has their own wide adoption in multiple use cases. And then we have the set, which, well, by now, you know what is a set from Lab 5. It's just simply an ordered abstraction data type, right? This is already existing in the STL. So, Kurt, does map compare to the direct dictionaries in Python? Well, in a sense, yes, and in a sense, no. there might be the closest, but dictionaries in Python might allow you, to my understanding, to have that every single entry can be of different kind of structure, right? Uh, so in other words, the key and the value does not have to be consistent in dictionaries, right? Or how many values you store per key, right? So it's an irregular data structure in a sense, right? But the map in C++, the key has a well-defined type, the value has a well-defined type, and how many values you store by key also have a well-defined type, right? So you can think of dictionaries as a map of maps, for example, right? Which is also people kind of implement in C++ using map of maps, right? Okay, so we have seen some examples of containers or abstraction data types. What about algorithms? So you need something to operate on them. For example, find or search for an element similar to what we have done on linked list last lecture, maybe merging two different containers or two different linked lists, think about this, or merging two different sets as you do in lab 5, maybe reversing the order, sorting, maybe counting, removing elements, deleting, rotation. There might be multiple algorithms that in fact operate on data structures. So all of this seems fine, but let's have some sort of an example, right? Some sort of what is a container, how we deal with it, right? The simplest container is the vector in STL. Again, what is a vector? It's just the dynamic version of the array because it can self-grown and self-shrink because, well, inherently it's in fact a dynamic data structure. And usually people in most of the professional code I have seen, maybe aside from very low level embedded firmware, people use vectors, right? Because it's quite dynamic, quite versatile, and can grow and shrink. So it provides a good utilization of the memory. On the other hand, because it's dynamic, people in embedded firmware don't really prefer it as much because it has its own risks of, well, again, dynamic behavior, which some of these systems don't really prefer. Good. So remember that we said containers are templates, right? So every single container type can in fact hold any data type using templates from past lecture. How they do this? Well, we have already seen this from last lecture of templates, right? So vector int will be a vector of integers, vector string of strings, vector end pointers, in fact, will be a vector of pointers to integers. I mean, vector, and this is the last one that is critical. All of these are user-defined types, right? But in fact, you can have a container of user-defined, sorry, all of these are built-in types. While the last one, the shape class that we have written 2 weeks ago, is your own user-defined class, and you can have a vector of user-defined types, right? That's also key there. For example, if you remember lab 3, by the way, something that's very interesting. I would like if I could have the time to really do it in 2SH, but because we don't have time, maybe try on your own. It's a good exercise even to prepare for the final. Is in lab 3, you implemented this student sort of database using structures and arrays, right, and pointers. What if you want to re-implement the lab using, well, classes, right? And then in that case, you use pointers and classes, and then maybe you also have another version that implements containers and classes, like something like a vector of a student, right? Or a 2D vector of students, if you would like, right? It will be very interesting to see how it's easier to implement in C++. Dino, and there is a question. Since vectors grow dynamically, are the elements still stored side by side in the memory like an array, or they can anywhere in them? Yeah, that's a good point. Any dynamic data structure, Dino, cannot be guaranteeing that it's back to back, right? That's the key, right? Uh, because you don't determine the size from the beginning, so you don't know how much to allocate, right? Unless the allocation happens. So to be honest, I don't recall exactly how the vector is inherently implemented, which is, by the way, publicly available. You can check this in the C++ reference. But what I recall, let me check, is the vector implemented internally using one malloc for the whole data structure, and this guarantees back to back. I guess I need to get back to your question based on, because it might be that case, right? You start with a certain malloc, which is dynamic type, and then you reallocate if you need something larger. And in that case, it will take more time. This is what I recall how vector is being implemented. So elements are still back to back. And that's one clear distinction between vector and list, because I told you already that there is another data structure called list, right? List is implemented using a doubly linked list in C++. So I know for sure that lists, in fact, are elements are not stored back to back. But vector, if I remember correctly, uh, their implementation is back to back by using one big malloc, and then you reallocate if you need a larger size, right? So that's my understanding. But I guess I will get back to you. Maybe by the end of the lecture, we can look this up together to show you also how to kind of look for any information in the reference manual if we do recall it. Good. So how to use it? Well, simply any container you want to use, you should be including its header file. So you include the vector. Uh, vector provides a mean, and this is the one reason why I kind of remembered it's that it's implemented back to back, because you can still use the vector exactly the same way you used arrays in C style, right? Or you can use it as if it's a class, right? STL style. So let's see both, right? Assume I just want to write a very simple example using a vector. So simply, and in this case, I'm using it as if it's an array, right? So this is array style example. I just define an object of my vector using the template int, and I call it I vector, while referring to an integer vector. And then now I kind of call the constructor that has the size, which is 10 right now. And then I iterate through my vector element by element using the index as if I am really indexing an array, right? And then later on, well, you can see, compare this one to this one. Within the same loop, I'm really iterating through the vector and I assign it to an array, right? So pretty much you cannot really differentiate the usage of a vector versus an array in that case, right? So if you want to use vector as if it's an array, you can still do so, right? This makes sense? The only difference is you just really declare it while using the template way we have done last time, because it's a template class or container in STL language. So, well, some specifics, the way you generally define it is you use the reserved word vector, and then you put your type within the template placeholder, and then the name of the vector. Now, if I want to operate on it in an STL style, then I use some of the built-in methods, not the array index. For example, if I want to insert something at the end of the vector, if I use it as an array, I have to move my index to the end and then assign it, right? Uh, but if I want to add something to the back of a vector, I can use the STL style, which is using a method called pushback, for example. So in that case, you push back to the end of the vector your element. In that case, it's a string. Basically, I'm reading the word from a user and then pushing it back. If I'm operating it on an integer, for example, if I come back here, I can really write instead of this for loop, I can eliminate this one and then say I vec dot push back. And then, well, first of all, I need to read cn, well, some sort of an integer from the user, let's call it x, and then I push back x here, right? So this will replace this thing. This is the STL style, and this is the array style. In STL style, I'm using the pushback method, while in the array style, I'm just really using the indexing to insert values similar to an array. Is there any question? Again, you might be a bit familiar with pushback from Python as well, right? Okay. Here we used, by the way, STL provides different means of insertion. Pushback is one of them, right? There is another method that is called size. Again, we have seen size already in a string, right? If I want to return the size of a vector, given that we said it's dynamic, well, simply you can just use the size method that gives you how many elements you have. So now to see you to show you how it really works, I'm revisiting, maybe that's the second example we have wrote in the course, right? In CBART, where we are reading some integers from the user, and then we sort them, and then we print the result, right? If you remember that example from maybe the third lecture or so. Let's see how we implement this example using vectors. So I want to read the inputs, basically store them, and then sort them, and then return them back, right? So this is basically how we do it in the example. First of all, I define my vector exactly the same way we have done it before, right? You use a template, so and then simply you say it's an int because you know your elements will be int, and you call it anything. It's just basically IVEC, any valid name. And then I start reading from the user, and then I push back to my IVECTOR, right? So here I'm using the STL style for insertion, right? Once I finished inserting from the user, I want to sort them. So I'm using another method from the STL library that is called sort. Sort is quite nice because it takes the beginning of what you want to sort and the end of what you want to sort, and it will sort it for you. So it already implemented the algorithm. Remember, STL had containers and had algorithms, right? A vector is an example of a container. This sort algorithm is an example of the algorithms, right? Remember that algorithms operate on containers, right? So here, sort takes the beginning, and later on we will learn that in fact, this begin and end is an iterator, which is the third component of the STL. So this is the first component, second component, and iterators are the third component. So it takes the first iterator, which is, you can think of it as a pointer of the first element. So here, this is my vector. After I inserted everything, if I want to sort the whole vector, I just pass the beginning of the vector and the end of the vector, right? So I pass a pointer to the beginning and a pointer to the end, call it 1 and 2, and then the sort will sort it for me, right? And then now I want to print it back, right? So assume that I want to print all the elements after sorted. How to do it? Again, I can do it the array style where I define a point, where I define an index starting from 0 up to a size and then print it one by one. Or I can use iterators or the smart pointers. How to do it? Well, you define an iterator, and this is basically you can think of it as a code template. I don't want you to use the word template because it's a overloaded word now, but you can think of it as a code snippet that is very, very common in operating on containers, right? You define a loop for iterators. You start from the beginning of your data structure or container until the end of your container. So you say iterator equal to the beginning. As far as iterator is not equal to the end, I increase my iterator. If you are confused what is an iterator, just a normal pointer. Think of it as a normal pointer. It's called a smart pointer because it has different capabilities, but think of it as right now it's just a point, right? How to define this iterator? I need to know this iterator will work on which data structure, on which container, right? So this is why now the way I define the iterator, it's an iterator of type vector of int because it's going to operate on ints, right? And then once I define it, I just have this loop very similar to a loops that operate on pointers. And then because I want to print the values, remember that this is our dereferencing operator that takes a pointer and turn the value that is pointing to. There is a lot here, so let me stop and take questions. Yeah, remember pre-incrementing or post-incrementing doesn't really matter in loops, Stefan, right? We have already had these two examples interchangeably in loops. In loops, whether you pre-increment or post-increment, it wouldn't really matter, right? Because the whole loop is one statement, right? Right. So try this out, try it with post-increment. You'll find that in fact it doesn't really provide a difference. If you are confused, make it a post-increment. So that's also okay. Yeah, thank you. Other question, please ask questions because I know this is a new topic. It seems might be putting so many things together, pointers, data structures, containers, templates. But that's the nature of programming is once you know a skill, you really combine it with another skill and you have more advanced topic. So ask questions, right? And as I said, this piece of code, if you understand it, well, it makes your life much easier looking into any other professional code that uses STL because it's very common there to iterate through data structures. Questions? Okay. So we have already used here examples of well, some of the methods of the vector class, including pushback, begin, end. All of these are just methods, right? What else? Yeah, end here as well and begin, right? So there are other operations or methods in a vector, including, for example, empty, which returns to you true or false if your vector is empty, because we said vector is a dynamic data structure. So in that sense, at some time, if you keep removing from it, it might become empty, right? And then in that case, you check whether it's empty or not. And then pushback, which we have already seen, that takes an element and push it at the end of the vector. And then basically, well, we have erase, which is delete for us, right? Uh, Basically, delete takes an iterator, and well, iterator is basically a pointer to a certain element, and then delete that element, and or maybe delete a chunk, which in that case takes a first and a second, and then delete it, right? And then clear basically deletes the whole thing. Good. So I don't want to start another example container. Before maybe I will show you another piece of code. Uh, so let's jump to uh, this example code here. What I'm sharing, I'm not sure what I'm sharing right now. Just share window, this one. What are you able to see? Let me see here. Okay, so you're able to see my code, so that's good. So basically, I will share, that's the list one. Oh no, let me open the vector one. So basically, I will share this code base with you, right? But that's an example of some operations on vectors in place. I can just copy the best and the code in online GDB and it will work. But I want to utilize the time to walk you some of it, right? So you'll observe first that I'm including the vector header file here, as we have already discussed, right? And then in the main, uh, well, I'm showing you here different examples of operating on or declaring vectors. The first one is I'm defining a vector of ents using templates. It's called v1, and then I'm initializing it using the same way we have initialized arrays before, right? Good. There is a helper function that we wrote here called print v. It's up there. What it does, it just basically prints the vector for us. So let's really go through it now to see how it works. So print v, it takes vector as an input, and then first of all checks if my vector is empty. That's one use of the empty function that I just showed you. Remember that in the past slide we have seen that empty returns Boolean. It returns true if the vector is empty and false otherwise. So if my vector is empty, I don't print anything, so I just return. Here, I'm using a simple format of for loop in C++ that simply operates on the vector. So what I'm doing right now is print v is a template method because again it operates on the template container. So I'm defining it as a template function. My type is t, right? Which by the way is int in our case, right? Because we have a vector of int, but generally it operates on any type vector because I want it to also apply in strings, etc. And then if you are confused with this loop syntax, which is pretty much similar to Python, we can write it another way. So I can say for what do I want to do? I want simply to maybe write iterators instead. So let me define an iterator. So in that case, we write it the same way we have done in the slide. So we'll just say I have vector, and now I operate on my vector template, and then I define an iterator, and this iterator I will call IT, okay? And then I would say for IT equal, what is my vector? My vector is v dot begin. And then I will keep looping as far as my iterator didn't reach the end. So it's v dot Oh, what is beginning here? Begin. Dot end. And then I increase my iterator. Right? That's basically how we operated through an iterator in our slide. And then what I want to do in my elements, I just want simply to print the elements, right? So here I will print my iterator value, maybe add a space. And once I'm done with my loop, I will just have an end line, right? So just do it that way and just remove this one, right? So is there any question how to use iterators in a loop, right? So this basically breaks down, this uses the empty method and uses the vector iterator. The interesting part here is, in fact, we are operating on an iterator of vectors without knowing what is the type of the vector, right? Which is kind of very, very nice using templates, right? Let me see if you guys have questions here. So you see that basically now I'm having this method that can operate on any vector, right? Good. So now this will print the vector, which will print those elements. And then I'm using some of the methods of a vector, like the size, for example, which will return the size, front, which gives you the front element, back, which will give you the back element. And then what if I want to operate on the vector using the index method of an array? Well, I can also use this. For example, getting the fifth element of the vector, I can just use v and then the index itself, 5. There is another method in the vector called add. This is a function. See here, this is array style, right? Array style, which is simply taking a vector name and the index in the brackets. This is now class style or container style, right? Well, usually people refer to it as STL style. Why? Because I'm using add, which is method, right? This is basically add is taking an index as an input and returns you the element at that. So if you open the vector implementation and look at the add method, you will find this is basically how it's being defined, right? Good. And then insertion, you can insert at a certain element. So assume, for example, I want to insert at the 5th element. I can also do it using array style by saying v1/5 equal 42. Basically, this again is array style. Or I can use the insert method that takes again an iterator, which is a pointer to the place where I want to insert, and the value, right? If I want to insert to the 5th element, this is basically beginning plus 5. Remember pointer arithmetic, right? And then that's the value that I want to insert. Good. If you try to print again the vector, you'll find that the 5th element, which is 0, 1, 2, 3, 4, 5, 6, now become 42. Erase is exactly the same thing, but because you want to erase so it doesn't take a value as an input, so you just simply say what is the iterator, and then you try to print it. You will find the new vector doesn't have anything. Pushback we have already seen, which adds a value to the end. Popback gives you the value of that of the last element, right? And then empty, again, checking whether something is empty or not, we have already used, right? And then clearing will simply clear the vector completely. Now using constructors, again, from C array style, we have already seen this. You can initialize that's again array style. Or I initialize things based on constructor. This is basically STL style. Right? So in that case, well, this is basically an array. So I defined a normal array. And then what did I do? I'm taking, yeah, okay. So this is basically STL copy style. So I'm copying values. You remember that we said constructors. One of them is called the copy constructor, where you take values. So I'm saying from the beginning of IA, what is IA? IA is an array name, which is a pointer to the first value, up to the array size, which is the end one. Copy all the values here to V2, right? So this is a copy style constructor. What else? Yeah, that's in fact all. So let's also try to run it, although we don't have much time. But I would rather walk through a complete example container than show you other stuff. So here, that's C++, and that's light here. And let me share the other window. So I'll stop sharing and then reshare line GDB. And yeah, so let's see what do we get. What do I have? 12. Need type name before. What does that mean? Oh yeah, because it's a template. Let's see if it's basically a template of that. Is that what we want to do? I'm not very sure, to be honest. Or I cannot. Let me see. What if I have done int here and run? And what about strings? Let me comment all of this out and run. Okay, so it operates. Okay, that's an interesting part because we want to operate. You know what? I want to show you really how to look for these problems. So what is the specific problem we're looking for? We want to operate on an iterator of a template, right? But we don't know the template. I'm not very sure why does it complain about that instead of having t, instead of having int, I'm having t as a type diff, right? Does it mean because I need to define my iterator also as a template iterator? So let's see that. Just say template. Type name t, and then operate on t. And let's try our odds. No, okay. So what I would do is, okay, what to look for. So declaring a template, declaring an iterator of a vector template. Okay. So here, okay, this is okay. That's exactly the same error we are getting here. So what is the problem? You need to say type name vector t. The other node, you are passing a vectors by value. That means the entire vector gets copied in the function call. Void show this, and using constant iterator would be wiser. Okay, so it's the type name itself because I'm coming up with a new type name. So let's see if that's really the problem we are facing here. So type name vector t and remove this one. Let's see what do we get. Okay, that's hold it all the time. Kind of works. So the reason is I need to, when I pass to this iterator definition, I need to tell that in fact T is a type name that is a placeholder, right? So this is basically operating using iterators on template containers, right? Good. And in that case, now I can safely remove the string stuff. Good. So what are we doing here? So I want to show you a line by line. Can I really separate this one? Well, let's go through it one by one. So the first one we had is just the initialization, right? Which is this one. In that case, let's just make it a little bit bigger. In that case, I'm printing the whole vector, the 10th elements from 1 to 10. Then here, what I'm doing a cout. So basically vector initialize thing. And then the size is just basically 10 elements. So I got the size of equal 10. I'm getting my front, which is 1, and my back, which is 10, right? So 1 and 10. And then element at 5. Well, this should add maybe something like this to make it readable. Then run again. So the element at 5 is 6. You either get it from the index or you get it from the add method, right? Just both gives you the same value. One of them is the array style, which is this one. The other one is your method style, which is STL style. And then for insertion, I inserted 42 in my 6 elements. So I'm kind of replacing here. Originally, I had 1 to 10, and then in this scenario, and that's one big thing I wanted to show you. For the array style, you go to the 5th element, which is what? 0, 1, which is 6 for you, and you overwrite it with 52, right? So 42. So in that case, you see that we have overwrote the 5th element with 52, right? Now, for insertion is a bit than overwriting, right? That's basically insertion, not overwriting, right? So what I want to do is go to that location, similar to what we have done for the linked list. Define the predecessor place. It becomes 42, and they insert at this location another 42. So we extended our array from being 10 elements to 11 elements by doing an insertion. And where did we insert? Well, after my 5th element. This is why you have a 42 and 42 here. You see that? So basically insertion is doing what we have done with the linked list in 2 lectures ago. Get the predecessor of the pointer, add the node afterwards, right? One array style is just overwriting. The question is, what if I wanted to do an actual insertion with the array style? So in that case, you want really to delete to shift everything. So you need to write a function that takes the array, start from the 5th element, push it back, like shift it by one element, free a place, and then add it, right? Okay. And then erasing is going to delete the 5th element. So I go back again to 42. And then push back, adding 47 to the end of the array. So this is basically 47. Bob back was going to remove the last element and give it back to you. So that's basically I removed 47. And then now I want to show you how clear really works. Let's see. I got 3 elements, so I printed them in a new array. And then for insertion, I'm adding at the beginning 1, 2, 3, 4, 5. And then print VX. That's 1, 2, 3, 4, 5. Oh, but these are print otherwhere. Oh, yeah, this one. The print after I bob back. That's a bob back, and then I get only 1, 2. I do another loop, remove the other one, which is 2, and then remove 1, right? Until my VX becomes empty. For clearing, I'm just really clearing the whole array, right? So at the beginning, the size is 5, and then after I clear, the size becomes 0. Good. So hopefully this example, I will share with you the full example. It walks you through some of the uses of vectors. I will also share with you the slides that contains also another introduction for the STL list, STL map for your own. This part you're not going to be tested on, but just is like an additional material to get you familiar with those other containers. They are just used exactly the same way. I see that we're already 4 minutes over, so thanks again for bearing with me, and hopefully this gives you a good pointer to STL libraries. Someone already had a question about Dainyuan, right? I'm not sure if you are still on the call. Yeah, you are already here. So if you want to stay for a second, let me show you really how to know vector implementation. in C++ STL. So in that case, how to implement your own vector? Okay, so let's see here. This really does not help because it just shows what we have already discussed. We want to see how it's being implemented. How vector is container is implement C++ STL. Dynamically allocated array. The memory for this array is allocated in the constructor. As more elements inserted, is dynamically increased. Yeah, exactly. So this is what I was saying. Okay, so it's being implemented using malloc in a sense, right? That's really how it works. Yes, here there is a delete. Okay, okay, okay. So you allocate. So to answer directly your question, you allocate, for example, here, you allocate certain size based on your copy constructor, for example, or how many elements you want. And then if you increase your size, it will do another malloc or reallocations. If you remember malloc and reallocation that we have done in C to increase the size. But what does it mean? It means that the container allocates the full chunk of the memory for the vector back to back. If you needed more space, it will do the deallocation and reallocation for you in the background. And this differentiates vectors from lists, for example, which are implemented as a linked list rather than being as a dynamically allocated array. Does this answer your question, Dainuan? This is pretty much what we said at the beginning. Is again, they are dynamically allocated, but back to back using malloc, right? Hopefully that's clear. Okay, so thanks everyone again, and see you next week.